Introduction to ALPN. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving deep into application layer protocol negotiation, commonly known as ALPN. This is a TLS extension that has become absolutely fundamental to modern web communications, particularly with the widespread adoption of HTTP/2 and HTTP/3. To understand why ALPN matters, let us first consider a problem that existed in the early days of protocol negotiation. Before ALPN, when a client connected to a server, there was no efficient way to determine which application protocol to use during the TLS handshake itself. This created delays and potential compatibility issues. ALPN solves this elegantly by allowing the client and server to negotiate which application protocol will be used over the encrypted connection during the TLS handshake, without requiring an additional round trip. Think of it like this. When you walk into a restaurant, instead of sitting down, looking at the menu, and then discovering they don't serve what you want, ALPN is like calling ahead and confirming they have your preferred dishes before you even make the trip. This negotiation happens within the TLS handshake itself, specifically during the client hello and server hello messages. The extension is defined in RFC 7301 and has become a critical component of modern web infrastructure. It is particularly important for HTTP/2, which requires ALPN for protocol negotiation. When used over TLS without ALPN, we would be stuck with slower, less efficient methods of determining which protocol to use. The beauty of ALPN lies in its simplicity and efficiency. It adds minimal overhead to the TLS handshake while providing crucial functionality that enables modern web protocols to operate at their full potential. How ALPN works. Let's break down exactly how ALPN operates during a TLS connection establishment. The process is remarkably elegant and efficient. When a client initiates a TLS connection, it includes the ALPN extension in the client hello message. This extension contains a list of application protocols that the client supports, ordered by the client's preference. For example, a modern web browser might send a list like HTTP/2, HTTP/1.1, indicating it prefers HTTP/2 but can fall back to HTTP/1.1 if necessary. The server receives this client hello message with the ALPN extension and examines the list of protocols the client has offered. The server then makes a decision based on its own capabilities and preferences. It is important to note that the server has the final say in protocol selection. This is not a mutual negotiation, but rather a server-side decision based on the client's offered list. If the server supports one or more of the protocols in the client's list, it will select exactly one protocol and include it in the server hello message via the ALPN extension. The server must select only one protocol. It cannot provide a list or leave the decision to the client. If the server does not support any of the protocols the client offered, it has two choices. It can either omit the ALPN extension from the server hello entirely, signaling that no application protocol was negotiated via ALPN, or, in some implementations, it may choose to terminate the handshake with a fatal alert. The specific behavior depends on whether the client indicated that ALPN negotiation was mandatory for the connection. Once the protocol is agreed upon during this handshake phase, both the client and server proceed to use that protocol for all subsequent communication on that connection. The entire ALPN negotiation adds virtually no latency because it is integrated into the TLS handshake that would happen anyway. This is vastly superior to older methods like NPN, which required additional round trips, or application layer protocol negotiation, which happened after the TLS connection was established. With ALPN, by the time the TLS handshake completes, both parties know exactly which protocol they will be speaking, and they can immediately start using it without any additional negotiation steps. This efficiency is crucial for performance-sensitive applications and is one of the reasons why HTTP/2 and HTTP/3 mandate the use of ALPN. ALPN Protocol Identifiers. Protocol identifiers in ALPN are standardized strings that uniquely identify application protocols. These identifiers are maintained by IANA in the TLS Application Layer Protocol Negotiation Protocol IDs registry. Each protocol has a specific identifier that must be used consistently across all implementations. The most commonly encountered identifiers include H2 for HTTP/2 over TLS, HTTP/1.1 for HTTP version 1.1, and H3 for HTTP/3. The identifier H2C exists for HTTP/2 over cleartext TCP, though it's rarely used in ALPN since ALPN operates within TLS connections. Beyond HTTP protocols, ALPN supports a wide variety of other application protocols. For example, there are identifiers for various messaging protocols, streaming protocols, and even database protocols. The identifier format is deliberately kept short to minimize overhead in the TLS handshake. Each identifier is transmitted as a byte string prefixed with its length, so shorter identifiers mean less data to transmit during an already communication-intensive handshake process. When implementing ALPN, it is crucial to use the exact identifier strings defined in the IANA registry. Even small variations, such as capitalization differences or extra spaces, will cause the negotiation to fail. This is because the comparison is done at the byte level with no normalization. This strictness is intentional. It ensures there is no ambiguity about which protocol is being selected. If you are developing a custom protocol and want to use ALPN for negotiation, you should register your protocol identifier with IANA to avoid conflicts with other protocols. The ordering of protocol identifiers in the client's list is significant, as it represents the client's preferences. However, as mentioned earlier, the server makes the final selection and is not obligated to honor the client's preference order. The server might choose a less preferred protocol from the client's list based on its own capabilities, load conditions, or administrative policies. This gives servers flexibility in managing resources and protocol support while still maintaining compatibility with diverse client implementations. Modern applications often implement dynamic protocol selection logic where the preferred protocols can be configured based on deployment environment, security requirements, or performance considerations. ALPN versus NPN comparison. Before ALPN became the standard, there was an earlier attempt at solving the protocol negotiation problem called Next Protocol Negotiation, or NPN. Understanding the differences between NPN and ALPN helps illustrate why ALPN was developed and why it is superior. NPN was originally developed by Google as part of their SPDY protocol initiative, which was the experimental precursor to HTTP/2. While NPN worked and served its purpose during the SPDY era, it had several significant drawbacks that ALPN addressed, which ultimately led to ALPN becoming the standardized solution, and NPN being deprecated. The most notable difference between ALPN and NPN is in who makes the protocol selection decision. In NPN, the server sends a list of supported protocols to the client, and the client makes the final selection from that list. This might seem democratic and client-friendly, but it creates several problems in real-world deployments. If the server's capabilities change or if the server wants to direct traffic to specific protocols for load balancing, resource management, or security reasons, NPN does not give the server that control. The server is essentially at the mercy of the client's decision-making logic. ALPN flips this model completely. The client proposes a list of protocols it supports in order of preference, but the server makes the final decision. This server-side selection is more practical for real-world deployments because servers typically have better knowledge of their own capabilities, current load conditions, and operational requirements. Another critical technical difference lies in the timing and encryption of the negotiation process. NPN's protocol negotiation happens after the TLS encryption is established. This means an additional round trip is required within the encrypted channel, specifically for protocol negotiation. This adds latency to the connection establishment process. ALPN's negotiation, in contrast, happens during the TLS handshake itself. It is embedded within the client hello and server hello messages that would be exchanged anyway. This means 0 additional round trips are required for protocol negotiation, making ALPN significantly more efficient. Furthermore, there is a difference in what information is encrypted during the negotiation. In NPN, the protocol list from the server is encrypted because it is sent after the TLS channel is established. In ALPN, both the client's proposed list and the server's selected protocol are sent in cleartext as part of the handshake messages. This might initially seem like a security regression, but protocol identifiers are not considered sensitive information. They simply indicate which publicly defined, well-known protocol will be used for communication. From a standardization perspective, NPN was never formally standardized through the IETF process. It remained a Google-authored draft specification that was implemented experimentally in various browsers and servers to support SPDY-ALPN. On the other hand, went through the full IETF standardization process and was published as RFC 7301 in July 2014. This formal standardization meant that ALPN received broader review, had clearer specifications, and gained wider industry acceptance. As HTTP/2 development progressed, the working group made ALPN mandatory for HTTP/2 over TLS, which effectively sealed NPN's fate. Modern browsers have completely removed NPN support, and it is now considered a deprecated legacy protocol negotiation mechanism. The transition from NPN to ALPN represents a maturation of the protocol negotiation approach, incorporating lessons learned from SPDY deployments and providing a more robust, efficient, and standardized solution for the modern web. Thank you for your attendance. Please consider subscribing to the channel.